Hello and welcome to part 2 of the rational exponents lesson video. We are going to start with some simplifying problems when it comes to rational exponents and applying them to different sorts of problems. So to start off with, we are looking at 8 to the power of 1/3. So the first thing I would do is change it into a radical, and that means that I'm doing the cube root of 8, which is actually a perfect cube. So that means that I can take that cube root of 8 and I can make it into just equal to 2. Now, technically, that -2 is not going to get you the same thing, which is kind of what people mistake that with when compared to square roots. So that problem kind of demonstrates how easy this can be. So let's move on to our next problem. In problem number 2, we are looking at 4 to the power of -3/2. So the first thing that jumps out at me is that we have a negative exponent. So let's make that change by putting it into the denominator, which is one of our exponent rules. So now we have 4 to the power of 3/2. So now from there, I can change that into radical form. So the one on top is obviously not changing. But on the bottom, we have the square root of 4, and we are going to cube that answer, because the numerator is 3. Now, I could have put the 3 on the inside, but something to look at is that sometimes you're going to have an easier way and a harder way of approaching these types of problems. When you are doing a square root of a number you know is a perfect square, like 4, definitely do it first. But if you're not sure, sometimes it's easier to cube it, and then it might end up with a number that is a perfect square afterwards. So now, if I'm going to continue, well, I know the square root of 4, this part in the center, that's is equal to 2. So if I write that out, now I have 1 over 2 to the power of 3. That 2 replaced the square root of 4 because they're equal. So now from there, I can write 1 over 2 cubed as 1 over 8, which is the final answer of this problem. Okay, we can move on to number 3 now. So let's keep moving through these problems. So now we are at 4x to the 4th to the power of 5/2. So the first thing that I'd want to do would be to try to move it into radical form. Actually, the first thing that I'm going to do is distribute that 5/2 to the two things in here, since I won't then have two different things under my radical symbol. So that means I have 4 to the power of 5/2, which we can deal with on its own. And now we have x, since this 5/2 went to both things in here, whenever you're putting an exponent on top of another exponent, that means you have to multiply those powers. So then I would have 4 times 5 over 2. So we're multiplying a whole number by a fraction, which means that my actual equivalent thing to what I'm starting with would be 4 to 5/2, and then the x would be to the 20 over 2, which we know is equal to 10. So now we basically have 4 to the 5/2, and we have x to the 10th. And that is basically the same thing as what we just did, as what we have so far. A positive result of us doing that first was that we got rid of any rational exponents on the variable part. Now we just have x to the 10th power, which is just done already. So we just got to figure out what's going on with the 4 to the 5/2 part. So first of all, we know we're going to do to the 5th power, and we're doing a half. So that means we're doing the square root of 4. So like in our previous problem, we're going to do the square root of 4 first, because I know that's 2, and then raise that to the 5th power. So that would become 2 to the 5th power, which our calculator would tell us is equal to 32. That means that my final answer of the problem would be just putting together the two ending results that we got, and that would be 32 times x to the power of 10. And that wraps up question number 3. So let's move on to question number 4 now. And we have 27 to the x times x to the 9th to the negative 2/3. So like last time, we want to take that negative 2/3 and make it positive. So the first thing I'm going to do is put it over a 1 and put it into the denominator. So now I have 1 over 27 x to the 9th, but it's being raised to the power of positive 2/3. Now that 2/3 is going to go on top of each of these two parts in the parentheses. So I have 27 to the power of 2/3. And I have x to the 9th. So I just got to do 9 times 2/3, which ends up being 18 thirds. And remember, this is all over 1 still. So let's look at the x part. So if I wanted to look at this x part first over by itself, I have x to the 18 thirds. 18 divided by 3 is equal to 6. So I know that x to the 6th would be the variable part of this that's going to go on in this fraction when we're done. Now with the number part, I have 27, and I know I'm doing the cube root of it, and I'm going to be doing it squared. Now, if I'm doing 27, I know that the cube root of 27 is going to equal to 3. So I'm going to put that squared on the outside. So I'm really going to end up with 3 squared being equal to that, which we know equals 9. And that means that my two parts of my answer are 9 and x to the 6th. And we just need to put that back underneath of our fraction. So our end answer equivalent to what we started with will be 1 over 9x to the 6th power. And that wraps up question 4. So we can make sure you take all this down, pause it. So let's get rid of it now and move on to the last part of our topic here. So we want to look through this first. So take a moment to pause your video and read through this on your own. Now that you've read through it, we are looking at trying to figure out how many Earth years does it take Mars to orbit the sun. And our picture tells us that if the Earth from the sun is 1 astronomical unit, which is 93 million miles, the Mars is 1.52 astronomical units. So it essentially is about 50% farther away from the sun than the Earth is. So if I know I'm trying to find the period P, so I need to use the D part for the astronomical units. So as an application of what we're working on here, you would take the astronomical units are 1.52, and you would raise that to the power of 3 halves. So you could put that straight into your calculator, but if it makes more sense to you, that is the equivalent of the square root of 1.52, and we'd be raising that to the 3rd power. So you'd have to use a calculator for this because of the decimal involved. So grab a calculator and put that in to see what you get. The answer that you should have arrived at would end up being 1.87. And remember, what we're finding here is the period in Earth years. So 1.87 Earth years will be the same thing as Mars, 1 year. So that's usually how much farther away the Mars is from the sun, and it takes that amount of more time to go 1 full rotation, which is a year for us here on Earth. Now, the problem isn't asking us about this, but it's an interesting way to interpret it is if What if we wanted to do the reverse of what we just did? Instead of finding the period, we would be looking for the distance. So if I know that Mars is 1.87 Earth years, what if I wanted to look for something that was 5 Earth years away, and I wanted to look for how far away something would be if their year takes 5 times longer than Earth's year? So this is not something that's directly in this chapter, but solving this sort of equation is something we'll work on in the future. So if I were to do this problem, my best way of solving this would be to kind of use solve an equation skill, kind of a reciprocal of the upside down 3/2 here. So if I raise this to the power of 2/3, we're doing a power to a power. So if you multiply 3/2 and 2/3, that would equal to 1. So we'd end up with d to the first power. So now if I wanted to do that to both sides, all I would need to do is 5 to the 2/3 power in my calculator to find my answer. And so you end up with d being equal to about 2.92. So that, remember, is the d part, is the distance from the planet to the sun in astronomical units. So almost 3 astronomical units. So you'd be doing almost 3 times 93 million miles. So that is getting up to be about 280 plus million miles away from the sun, which is quite a long distance. And that wraps up part 2 of our rational exponents lesson. Thank you for watching.